Okay, sorry about cutting off there. So basically in this part, I'm just going to get to the chase of what we're going to do in lab on Friday, October 6th. So like I said, each group, so you guys will come to lab at the assigned time. You're going to get an email from me saying you should be at lab at 1:30 or 2 or 2:30 or 3 or 4:45 or whatever. Come at that time. You won't have to stay for the whole 4 hours, but you might have to come late. So then you're going to run the assigned reaction, and there are several reactions. So there's going to be a bunch of reactions with butyl bromide, N-butyl bromide plus sodium iodide, and the solvent is going to be acetone. All right, the solvent just sort of provides a medium for the reaction to happen in. It doesn't actually participate. But if you look at this reaction, which side is favored? All right, and I'll just cut to the chase. Carbon bromide bond is stronger than a carbon iodide bond. Thermodynamically, the left side of this reaction is more stable. However, sodium iodide is soluble. Sodium bromide is insoluble in acetone. So keep that in mind. Just make observations, right? You're going to run this reaction. You're actually not going to have to work very hard in this experiment to do the experiment. So which side is favored? Which protons we're going to look at. But like I said, 3 or 4 groups are going to run N-butyl bromide plus sodium iodide and acetone. One group is going to run T-butyl bromide plus sodium iodide and acetone. Another group will run N-butyl chloride, where iodide is going to substitute for a chloride. And yet another group will run sec-butyl bromide plus sodium iodide. Okay? So for N-butyl bromide plus sodium iodide and acetone, there is one reaction rate constant. It's the same reaction. All we're going to be doing is changing the concentration of the reagents. So that will change the rate. For these, are different reactions. Right? So T-butyl bromide plus sodium iodide is different than N-butyl bromide plus sodium iodide. So the reaction rate will be, the rate constant, K, will be different. So that's why we're going to basically measure reaction rates using NMR. Like I said, as the last video cut off, you're going to come to lab, you're going to mix the reagents. So we'll have stock solutions of all these things. You'll mix the reagents as described. Shake them up, quickly put the sample in the NMR machine. We'll run an NMR every minute. So these are the time points, right? Time point is just when we run an NMR. So we run an NMR, wait 60 seconds, run another NMR, wait 60 seconds, run another NMR. After 10, 15 minutes, we'll run them every 2 minutes, and then we go out to about 30 minutes to an hour. But you'll get 15 to 25 time points per reaction. So your TA and I will process the initial data, take it off the machine, and give you some raw data. The raw data are just going to be numbers. Okay, so you will have an integration for one of these signals. You should again think about which one would be good to use. You'll have integration for one of these signals, and then in the lab write-up tells you how to normalize that. But basically, the sum of the integration. Let's just say, for instance, that we use the CH2s bonded to the halide, right? You get an integration for this one at time 0 and an integration for that one at time 0. The sum of those integrations has to equal the concentration. I will write that down over here. Going to equal the concentration. This is all right. The sum of the integration for the reactant and the product in the NMR has to equal the initial concentration. So that's your normalizing. you're going to take this raw data that Natalia and I will post, and you'll analyze it. So you're going to run plots in Excel for your group's data. So if you do in-butyl chloride and sodium iodide, that's the data you process. You'll run these three plots, concentration of A. A in this case is going to be the halide, the alkyl halide. Right, so in-butyl chloride, T-butyl bromide, whatever, that's A. So you're going to run concentration of alkyl halide versus time, reciprocal concentration of alkyl halide versus time, and the natural log of the alkyl halide at time t versus time. You're going to see which one gives you a linear plot. That'll give you the reaction rate order and the slope. Right, the slope is going to equal either k or minus k, depending. And then you're also going to do, I erased the initial reaction rate. You're also going to plot the first 2 to 4 time points for concentration of alkyl halide versus time. All right, that's an initial rate. And I say 2 to 4. 2 is not many data points. It'll be a line, right? 2 points define a line. And that'll give you the slope that is k or minus k. It's minus k. But as long as it's linear, maybe the first 4 time points will be linear. You want it, you're going to get a plot. This plot will be, so A, T, this is time. That's going to be how the plot looks. The initial rate is that slope, the slope early on, right? So that's what we want to get, the initial rate. The initial rate is going to give us the overall reaction rate, the change in concentration versus time. And so then, by comparing that initial rate for in-butyl bromide and sodium iodide and these 3 reactions down here, you're going to be able to get relative rate constants. Where did I put that? Relative rate constants for in-butyl chloride, sec-butyl bromide, and T-butyl bromide. Right? And so for this relative rate constant, set in-butyl bromide with sodium iodide equal to 1. And so the question is, does in-butyl chloride plus sodium iodide react faster or slower than in-butyl bromide, right? The change here is Br and Cl. Chloride react faster or slower than Br? Here you're changing the carbon that the halide is on, right? So up here the bromide's on a primary carbon, down here the bromide's on a secondary carbon. Which one of those molecules reacts faster? So you can get that. If the initial reaction rate for sec-butyl bromide is greater than the initial reaction rate for n-butyl bromide, it reacts faster. Same thing for T-butyl bromide. All right, very important. You're going to run these plots, and you're going to upload your data by October 16th. I'm going to say this a lot in class and lab. If you don't upload your data, your plots, by October 16th, then you will receive a 50-point penalty. So basically, you'll get no credit for that. We'll talk about this more in class, in lecture class on October 17th. And then you'll have a worksheet and a report due on this on October 20th. So the fall break is October 13th. We won't have lab or class. We won't have class on October 12th. We won't have lab on October 13th. Okay, so you guys have messed with videos before, right? So you can go back and play this. You can ask me questions. But the important thing is you're going to come to lab. We're going to basically, Natalia, Dr. Wright, and I will run this reaction with you. You're going to have to stand there and monitor it. Then we'll upload raw data. You're going to use this equation. The sum of the integrations has to equal, for sum of the integrations for n-butyl bromide, n-butyl iodide, it's going to equal the initial concentration of n-butyl bromide. And then this will give you, from that, so you'll sum these up and get that, and then feed that back in here to give you the concentration of N-butyl bromide at time t. And that's what you use to plot. That's going to be A in these reaction rate plots. So Natalia and I will integrate these over the weekend by Monday, October 9th. So we're going to do this live on October 6th. By Monday, October 9th, you'll have the raw data online. You go in and run plots in Excel over your fall break. And then you upload your data. And your data is going to be, that's an important thing, K reaction rate, a plot, sorry, a linear plot, so that's the data you're going to upload. You're going to upload a reaction rate constant. You're going to get that from the slope of your linear plot, and you're going to upload the linear plot. And then, after everybody's data is online on October 16th, you're going to use that data. You're going to use everybody's data to determine the reaction rate order of N-butyl bromide plus sodium iodide. So that's the reaction rate plots, looking at various concentrations, how changing the concentration of reagents affects the reaction rate. And then you're going to determine the relative rate constant for these other three reactions. Are they faster or slower? All right, so most of this lab is not in lab, and that's the way science works. Okay, so most of us, when we think about doing science, we think about time in the lab, time at the instrument. Most of it's data analysis and thinking and playing with numbers. Actually acquiring this data is not going to take very long. You'll come in, like I said, in a group of 4 or 6 on Friday, October 6th. You will, basically, a couple of you will mix some chemicals up, hand an NMR tube to Dr. Wright. He's going to run the NMR. We're all going to stand there and watch it. And then Natalia and I, and the reason Natalia and I are processing the data is it's specific software. We'd have to teach you how to use the software. It changes every couple of years. There's no reason for you to learn the software at this point. So we'll get the raw data out. She and I can do that pretty fast. We'll plot that, we'll upload that to Google Sheets, and then you guys will play with the data. And playing with the data is a lot of what science is. All right, go back and rewatch this, pause it, take notes. We'll be talking about these reactions, these substitution reactions, probably starting Thursday, August 5th. So we probably won't get to it today. I'm filming this on Tuesday, October 3rd. 2 days from now, we'll probably start talking about substitution reactions in class. And then we'll be talking about substitution reactions for a while, so you'll see a lot of this. Okay.